Hi, and welcome back to my videos for Physical Chemistry 1. For the past few videos, we've been looking at Maxwell relations, and we've seen that they can help us calculate thermodynamic properties like the entropy and Gibbs free energy from properties that are much easier to measure experimentally, like the pressure, volume, and temperature. But there's one important shortcoming in all Maxwell relations. We derive them all from gas laws, so they're really only meant to be applied when our system consists of one or more gases. What happens when the chemical process we're looking at involves other phases, or when the phase changes during the process? That's a very common situation. After all, most of the chemical reactions you've probably done in chemistry labs have involved liquids and solids. So that's what I want to talk to you about today. It turns out that the Gibbs free energy makes some interesting predictions for processes where the phase of our system changes. To begin, let's think about the simplest situation we could have for a system consisting of two phases. We have just one substance and hold the pressure and temperature constant at exactly the right value so that the two phases of the substance are in equilibrium with each other. So, for example, if the substance in our system was water, we could hold the pressure at 1.00 atmospheres and the temperature at 100 degrees Celsius, so that the liquid and vapor phases would coexist and be in equilibrium. Alternately, we could hold the temperature at 0 Celsius and have the liquid and solid phases in equilibrium. And if we carefully chose a different pressure and temperature combination, it would be possible to have the solid and vapor phases in equilibrium. It's even possible for a substance to have more than one different solid phase. For example, water actually has 18 different solid phases, although most of the solid phases, except for ordinary ice, are only possible at very high pressures, over 1,000 atmospheres. Anyway, we'll call the two phases that are in equilibrium phase A and phase B. Since the system is at equilibrium, we know that dG is equal to 0. But now, suppose we disturb the equilibrium slightly. For example, by changing n moles of the substance from phase A to phase B. In that case, dG will no longer be equal to 0. How can we determine what it is, assuming we don't have access to a table of data for the Gibbs free energy? To find the answer, we'll use something we learned back about in video 29, the total derivative. As you might recall, we take the total derivative by differentiating our function, in this case the Gibbs free energy, by the variables in the system. In this case, we're holding the pressure and temperature constant, so those aren't our variables. What properties of the system are changing? Well, we said we're changing some of phase A into phase B, so our two variables are Na, the moles of phase A, and Nb, the moles of phase B. So to get the total derivative of G, we take the partial of G with respect to the moles of A times dNA, plus the partial with respect to the moles of phase B times dNb. Notice that the subscripts on the partial derivatives remind us that we're holding T and P constant. We can make a slight simplification here. There are only two phases in the system, so the decrease in the moles of phase A must be equal to the increase in the moles of phase B. In other words, dNA and dNb must be the same number, but opposite in sign, so we can replace dNb with negative dNA. Once we've done that, we can factor dNA out of the two terms of the equation. It turns out that the quantities represented by those two partial derivatives are useful and important thermodynamic quantities. In fact, they're important enough to have their own name and their own symbol. The partial derivative of G with respect to the moles of a substance is called the chemical potential, and it has as its symbol the Greek letter mu. So the first partial derivative in our equation can be written as mu A, and the second one is mu B. When the system is at equilibrium, mu A and mu B are equal, so the term in parentheses is 0. That gives us 0 for dG. So if the system is not at equilibrium, that means that the two chemical potentials must not be equal. There's only two possibilities. Either the chemical potential of A is larger, or the potential of B is larger. Let's think about each of those possibilities for a minute. If A has the larger chemical potential, that means that the term in parentheses must be a positive number. However, for a spontaneous process, we know that dG must be negative, so D and A must be negative too. In other words, if phase A has a larger chemical potential, it means the amount of A must be decreasing. In contrast, if the chemical potential for phase B is larger, then the term in parentheses must be a negative number. Again, if we're looking at a spontaneous process, we know that dG must be negative, and that means in this case, D and A must be a positive number. So, in other words, if phase B has a larger chemical potential, the amount of A increases. What all this is telling us is that for a system consisting of two components, matter flows away from the component that has the higher chemical potential. This is exactly like what happens when you have two electrodes with different electrical potentials. Electrons flow away from the electrode with the higher potential to the one with the lower potential, just as a substance with a higher chemical potential is converted into one with a lower chemical potential. Notice that the chemical potential is the change in the Gibbs free energy divided by the change in moles. As you might remember from several earlier videos, another way of writing a molar quantity is by drawing a horizontal bar above the variable. So we can write the chemical potential using the symbol G bar. A nice thing about the chemical potential is that because it's a state function and not a path function, we can use it even for processes where the pressure and temperature aren't constant. For that reason, let's try taking the total derivative of the chemical potential with respect to P and T. When we do, here's what we get. And we'll soon see that this is a very practical result. Here's why. Take a close look at the two partial derivatives in this equation. You might recognize them. Back in video 29, we saw both of these partial derivatives as intermediate steps when we were deriving some of the Maxwell relations. The first partial derivative is actually equal to v, and the second one is equal to negative s. Both of those are results that we got in video 29. If we plug those into our equation, here's what we get. So, what's so useful about this equation? Well, plenty. Think about what happens when our system consists of two phases in equilibrium. In that case, the two chemical potentials are equal to each other. That means that negative S bar dt plus V bar dP for one phase is equal to the same quantity for the other phase. Notice that the system is being held at one pressure and temperature, so P and T are the same for both phases. But the two phases will almost certainly have different molar entropies and volumes, so they need subscripts, and the pressure and temperature don't. Let's simplify this equation a little. We'll move both entropy terms to the right side of the equation, and both volume terms to the left. We can factor dt out of the entropy terms and dP out of the volume terms. Next, let's divide both sides by dt, and also divide both sides by the term in parentheses on the left side. When we do, we get this equation. Think about what this equation is telling us. The term in the numerator is the change in molar entropy when a substance undergoes a phase transition. And the denominator is the change in molar volume for that same phase transition. Let's rewrite those as delta S bar and delta V bar with the subscript trans to remind us that this is for a phase transition. So we can use this equation to determine the entropy of a phase transition as long as we know the molar volumes of the phases and how the pressure changes with temperature, all of which aren't too hard to measure experimentally. We can also get another, even more useful expression if we're clever. Recall that we have this equation for the Gibbs free energy. When our system is at equilibrium, we know that delta G equals 0. In that case, we can rearrange the equation to solve for delta S, which gives us this. We can now substitute this into the equation we had earlier to get this result. This is an especially useful equation, and in fact, we will use it in our lab if we haven't already done so by the time you watch this. In the lab, we monitor the boiling point of a substance at different pressures. When we plot the pressure against the boiling point, we get a straight line whose slope is dP over dt, which is equal to this. This equation is so widely used it has its own name, the Clapeyron Equation, named after the French physicist Émile Clapeyron, who developed it. Of course, not all phase transitions are equally common in lab. For example, we don't see solid-to-gas transitions or solid-to-solid transitions in very many experiments. However, transitions between the liquid and gas phases are pretty common. For that reason, there's one more equation related to phases, specifically for vaporization, that'll be helpful for us to know. To get there, we need to make two assumptions, but they're usually pretty good assumptions, so the result we get will still be very useful. First, we need to assume that the molar volume of a substance is much, much larger for the gas phase than for the liquid phase. That's usually a pretty safe assumption. For example, 1 mole of liquid water occupies about 18 milliliters at standard pressure. But a mole of water vapor occupies about 30.6 liters at the boiling point. That's an increase of a factor of about 1700. So, the point is that the molar volume of a liquid is negligible in comparison to that of a vapor. That means that the change in molar volume in this equation is about the same as the molar volume of the gas. The second approximation we need to make is that the gas behaves like an ideal gas. We don't have to make that approximation, but if we use, for example, the van der Waals equation instead of the ideal gas law, the mathematics we're about to do would be much, much more complicated. So, if we imagine we have an ideal gas, we can use the ideal gas law. We'll divide both sides of the ideal gas law by n, which gives us the molar volume of the gas on the left side. We'll solve for V bar, and that gives us an expression we can substitute into the Clapeyron equation. Next, let's divide both sides by the pressure, P. When we do that, we find that the numerator on the left side is 1 over P dP. That might look kind of familiar to you. You've seen this integral identity before. The integral of 1 over P dP is the logarithm of P. What can we do with that fact? Well, as you might remember from your calculus course, an integral and a derivative are reverse processes. In other words, if b is the result of integrating a, then it's also true that a is the derivative of b. If we apply that to this integral, we find that 1 over p dp is the derivative of the logarithm of p. Let's plug that into our equation. The result we get is another very common and widely used equation, and it too has its own name. It's called the Clausius-Clapeyron equation, and was developed by Émile Clapeyron, who we mentioned before, and the German physicist Rudolf Clausius. You may never have heard of Clausius before today, but you've definitely heard about his work. Clausius is actually the person who came up with the word entropy for the thermodynamic property that we've been talking about for the last dozen or so videos. So, how do we use this equation? Well, as it's written right now, it's a little hard to use because of the derivatives in it. However, it won't be too hard to get rid of those derivatives and end up with a more useful equation. Here's how. Let's get rid of the fraction on the left by multiplying both sides of the equation by dt. Now we'll get rid of the derivative by integrating both sides. On the left side, notice that the variable we're integrating over isn't p. Instead, it's the logarithm of p. That may seem like a strange thing to use as the variable of integration, but it actually doesn't make the integral any more difficult to perform. The result on the left is just the logarithm of p2 minus the logarithm of p1. Using the rules we know about for logarithms, we can change this to ln of p2 over p1. Next, we'll integrate the right side. Delta h bar and r are both constants, so we'll take those out of the integral. When we solve what's left, here's what we get. This is a very easy-to-use equation, much simpler to work with than the Clapeyron equation. And in fact, this equation is by far the most common way of determining the enthalpy of vaporization for a substance. If that's something you ever need to do in the course of your future research, this is the equation that you want to use. Let's try to use it. Suppose we want to know the enthalpy of vaporization for metaxylene. At standard pressure, metaxylene boils at 139.12 degrees Celsius. But if we reduce the pressure to 100 millimeters of mercury, it boils at just 71.88 degrees Celsius. What would be the enthalpy of vaporization for metaxylene? To find out, we'll use this equation. The only thing we need to be careful about is the units. We need the temperature to be in Kelvin, not Celsius. If we plug all that data into the equation, here's what we get. Notice that I didn't change the units of pressure, even though millimeters of mercury isn't the usual SI unit of pressure. That's because the units of pressure are going to cancel out in this fraction. We could change the units to atmospheres or pascals, but since the units are going to cancel out, we get the same result in any case. Anyway, the quantity in parentheses is equal to 4.727 times 10 to the negative 4 kelvins to the minus 1. The logarithm is equal to negative 2.028. If we now solve for delta H bar, we find that the enthalpy of vaporization is 35,670 joules per mole. Notice we got a positive number here. That makes sense because we have to add heat to the substance in order to vaporize it. So it makes sense that this is endothermic, meaning that it has a positive enthalpy. There's one last thing to keep in mind. The Clapeyron equation and the equation we derived from it should only be used for systems that are undergoing vaporization. It's not valid for phase transitions involving liquids and solids, such as melting and freezing. If you think about it, you'll see why. We made two assumptions in order to derive the Clapeyron equation. First, we assumed that the molar volume of a vapor is much larger than that of a liquid. And the second assumption is that the system behaves like an ideal gas. Neither of those assumptions would be valid if we were looking at a phase transition that doesn't include a vapor. Well, that's enough new material for today. You've learned a lot, and that's because there's a lot to know about phases. We'll spend the next video delving more deeply into phase transitions and what we can learn about them. I hope you'll join me for that. But until next time, have a good week.